So this is the open hardware track. And defining what open hardware is both incredibly simple and also as complicated as it is to define open source. So the first use of the term open hardware is actually slightly older than open source. In 1997, Bruce Perens, who you saw on the keynote stage earlier today, launched the first open hardware certificate program. It was a year later that the first use of open source was applied to software. Open source was used to talk about intelligence in the CIA and things like that, but to talk about software, open source wasn't used until 1998. And also, free software was, of course, around since the 80s. So, but in terms of terminology, open hardware is slightly more mature than open source. However, the development timeline of open hardware has been much slower and much longer. And there are reasons for that, partly just because there are certain aspects of physical devices that are harder to do open than software. So there is a formal definition for open hardware, just like there is for open source. And it is tangible artifacts, machines, devices, or other physical things, where the design has been released in such a way that anyone can make, modify, distribute, and use those things. This probably sounds very familiar because it was written by Bruce Perens, who also wrote the open source definition. So what can you do with open hardware? The fundamental definition of open hardware is based on these rights that are granted to you. You can use, study, modify, and redistribute it, just like open source software. So what gets released with open hardware? Now this is a little bit more complicated. Fundamentally, it is anything that you need to exercise those rights to use, study, modify, and redistribute the hardware. But the concept of source is a lot more varied for hardware. You know, it isn't just as simple as, well, you release the Python language sources and boom, you're done. Sometimes there's a lot more to it. And within the realm of open hardware, we have this concept of available components, which was defined by Andrew Katz, which you may have heard of if you've worked in open hardware. And that is, in hardware, sometimes you hit a point where there are things that simply are not available open. It could be little things, but it also could be as big as, like an Intel chip, right? Like, it's just not available as open. So as long as those things are readily available to purchase, we will accept that it's still open hardware as long as people can get what they need to make their own copy and modify it and redistribute it. The benefits of open hardware are actually exactly the same as open source. Things like open innovation, once people share their knowledge and experience and best practices and code and design and implementations, then they can leverage that collaboration to accelerate innovation, to do things better and faster than they could if it was just on their own. And in some ways, this should be obvious, right? Like society, civilization is built on the idea that things are better when we do them together, but somehow in technology, we got the idea that it would be better if we could just lock it all away in one little company with only the people that company hired and only their knowledge and only their experience, and somehow that would be better. It doesn't make any sense, but we got that idea. So with all of open technology, we're kind of reversing that idea, and civilization is better when we work on things together. There are also benefits to transparency. When things are in the open, you can inspect them. You can understand how they were made. You can learn from them. You can build on them. And ultimately, open technology, both open source and open hardware, is a public good. It is available to absolutely anyone, individuals, academics, governments, companies. It is not exclusive, and it is not rivalrous. And all the other benefits that you will hear about in the next 2 days here about open source, those are also true about open hardware. So, an open source, we're used to this clear definition. Open source is software released under an open source software license, generally approved by the Open Source Software Initiative. And across the full stack of open source software, we share programming languages and tools for, like compiling and testing and verification. And generally, that's where the diagram stops. And you just see this generic box underneath that says hardware. So this track is about expanding out that box of hardware into the full range of the stack of hardware. Now, both hardware and software here are abstracted. There's a lot more detail here, but this is an overview of the whole field. So in hardware, you also have licenses, but there are different kinds of licenses. There are open source hardware licenses, but those are typically applied to the realm of devices and boards. There are also open source software licenses applied to certain elements of this hardware stack, because some things are actually released as like chisel source code, which kind of is source code, except it's used to build hardware. You will also see documentation licenses or content licenses like Creative Commons, because sometimes you have like a diagram of how to build the server hardware, or you'll have a specification document released under a documentation license. The tools are also a lot more varied in hardware. So each level of the stack has different tools. There are similarities, right? Like all of these tools are about building and testing and verifying the hardware, but there's a much more broad spectrum of different kinds of tools that are used. So on the software side, we're used to the fact that you can have combinations of open source and proprietary software. For example, you might run Firefox on Windows. You might run Zoom on Linux, so you have a proprietary application running on an open source operating system. Even if all your applications in the OS are open source, you might end up needing some proprietary graphics drivers, or even if all your drivers are open, you might end up needing proprietary firmware. And even if all your firmware is open, like Coreboot, you may still have some proprietary blobs buried down inside there. So on hardware, it is similar. So that first open hardware certification, and most things you will see now that are open hardware certification, are in the realm of devices and boards that are open, but use proprietary components. So like there is a layer of open, and then below it there is a layer of proprietary, just like proprietary drivers or firmware. You will also see more tomorrow. Open compute is a term that you will see used, and what that tends to mean is basically the same as open hardware certification, in the sense that it's focused on devices and boards that are open. Anyone can use, study, modify, and redistribute them, but they will use proprietary chips and components. You'll use an Intel chip in an open server that's otherwise open. So open compute is usually in the realm of servers in data centers, not smaller devices. Another thing that you see is you will see open instruction set architectures, ISAs, like RISC-V, where all that's open there is the standard. So we call that open standards. We don't really call that open hardware, although it is part of the realm of open technology in the domain of hardware. So we do talk about that here, but you need to be a little bit careful about not saying that's open hardware. So if you've only described the instruction set architecture and released that as an open standard, we would call that an open standard. But once you implement that as a microarchitecture, so a standard just describes how it works. It's kind of like saying we released all the function names as open source, but we didn't actually implement any of those functions. So the microarchitecture is like, okay, now we implemented all those functions. It's a full working implementation. At that point, we call it open silicon, because what we're defining is silicon. We may still not call it open hardware. Yeah, it's a little bit fuzzy at that point. You may call it open hardware, you may not. Open silicon is also if the entire chip or SoC, so system on chip, which is like the chip plus components, is open, then at that point you would certainly call it open silicon, and you might also call it open hardware. But then, even if your entire stack, applications all the way down to the microarchitecture is open, one of the challenges in open hardware is, for now, a lot of the tools are still proprietary. So we're kind of stuck in this space, unlike open source, where you can always use GCC, you can always use Verilator, verification tools for checking your source code. You can use testing tools. You can use, in open hardware, there are some open tools available, and they're getting a lot better. That's part of what is changing now. But there's still a long way to go in terms of being to build a fully open hardware system with entirely open tools. So the track that we have for you is covering the full spectrum. Our first day, it kind of has a little bit of everything. We have some about devices and boards and chips and ISAs and microarchitecture and tools. The second day is focused more on the devices end of the spectrum, and especially it'll be a lot about open compute, about open hardware in data centers, open servers in data centers. But it does also have a little bit about some reflections on open firmware, which, while it is software of a sort, it's so tightly coupled with the hardware that we often have to talk about it with the hardware rather than over in the general open source area. And then also a little bit of talking about open hardware in the context of open science. So I hope that helps make a little bit more sense about it. You look at a track like, there's no way we could cover all of open hardware and all of open technology and hardware in a track. But we can give you a little sampler, a little taste test of all the different areas that are important to open hardware.